Take a look at this high-performance engine block. If you are an engineering lead today, choosing which of these power plants to drop in feels like the most critical decision you can make. The reality is exactly the opposite. Spending your cycles debating which frontier AI model is superior is a strategic dead end. The top models on the market are rapidly converging towards strict parity. They share the same baseline capabilities, the same massive context windows, and the exact same price floors. These frontier models operate as literal commodities. They are extraordinary feats of engineering, but they are also identical, sealed units, available to every one of your competitors on the exact same day you get access to them. Any narrow advantage one provider achieves over another closes almost immediately. The capability gaps vanish in a matter of months, far faster than your engineering team can build out a business model to exploit them. We are operating in a market with an aggressive inverse relationship. The raw computational capability of these models is converging rapidly upward, while the defensibility of building on top of them is dropping to zero. Staking your market differentiation on the fact that you use a specific top-tier model gives you zero actual leverage. You are simply holding a standard software subscription that everyone else in your sector also holds. The industry relies heavily on Formula One to explain AI competition. People assume they are competing like Mercedes or Ferrari, where proprietary engineering inside the engine block wins the championship on raw horsepower. That mental model is flawed. Watch this grid of diverse engines. Notice how it morphs into a uniform line of identical, sealed blocks. We are not in an F1 race. We are in a spec racing series, like IndyCar or NASCAR, where the series rulebook mandates that every single team use the exact same homologated power plant. Spec series enforce this identical hardware for a specific reason. It forces the competition entirely off the engine and onto the surrounding components. Teams win based on the chassis, the tuning, the telemetry, and the strategic execution around the power plant. The frontier AI labs are quietly doing the exact same thing to the application layer. By converging their models toward parity, they are inadvertently writing a spec racing rulebook for the entire software industry. This hardware convergence forcefully shoves every remaining ounce of competitive differentiation out of the model itself and up into the application layer that surrounds it. We call this specific discipline harness engineering. It is the systematic craft of building the chassis, refining the telemetry, and tuning the entire system around a standardized engine block. In a spec series, having a fast engine means nothing, because everyone has one. The ultimate victor is always the team that executes a most refined craft around an engine that nobody on the grid actually controls. The harness is everything in your stack that is not the model. Because the models themselves depreciate with every new release, your harness is the only engineering asset you possess that actually compounds in value over time. It relies on 5 distinct architectural subsystems. The first is aerodynamics. A stream of data exits the engine block. One side hits a barrier, while the other funnels into its target. This is your prompt architecture. Sloppy instructions create drag, causing tokens to scatter, dissolve, and burn compute without hitting the objective. Aerodynamic optimization requires the disciplined, low-drag routing of information, ensuring 100% of the engine's output reaches its intended target. The second subsystem is the chassis. This is your codebase and system architecture. A stiff, modular chassis prevents the system's logic from warping under the torque of unpredictable model outputs, holding firm against high-speed pressure. While disorganized codebases break alignment, a rigid architecture ensures the structural load of high-volume tool calling is safely transferred to the objective without failure. Third is the suspension, per-engine tuning. This layer is frequently overlooked by operators who believe models are interchangeable components, requiring no individual calibration. Fourth is telemetry, your observability stack. You cannot tune what you cannot measure. Real-time traces, drift monitors, and robust evaluation suites are mandatory instruments. They are the only way to know whether to hold your current line or make a mid-operation tactical adjustment. The fifth and final subsystem is PIT protocols, your agentic workflows and automated governance. When a regression hits or a security flaw is exposed, you do not panic in the cockpit. You rely on out-of-cockpit agentic loops and strict procedural automations to handle race-critical events systematically. Integrating these 5 subsystems is the only mechanical way to convert raw, undifferentiated AI horsepower into actual, directed forward motion. The industry is currently obsessed with the idea of model-agnostic application wrappers. The promise is that you can keep your architecture untouched and simply hot-swap models whenever a cheaper one drops. Mechanical reality tells a different story. A chassis and an engine are co-designed. Zero-friction engine swaps are mechanically impossible because the raw output dynamics and stress fractures of every single model vary drastically under heavy load. Context handling, tool calling behavior, and prompt latency are inherently bound to a specific model's unique torque curve. Architectural balance requires 2 layers. This universal docking frame accepts the engine perfectly, but the springs beneath remain completely misaligned. The chassis acts as a stiff abstraction layer for bolt-on engine swaps, but the suspension must aggressively recalibrate its tuning to support every new model. Competitors attempting to maintain complete portability realize too late that they must tear down their entire infrastructure. They end up hand-rebuilding their entire foundation from scratch for every single new model release. True defensibility is not a system that ignores engine differences. It is engineering a specialized architecture where your per-engine retuning process becomes an operation that is consistently cheap, blindingly fast, and highly repeatable. This aftermath shot illustrates a common reality in modern AI development. An application produces one blistering hero prompt result for an investor demo, and then immediately breaks down and hits the wall under the sustained stress of a live production environment. Peak capability, the single fastest lap time, is a vanity metric. It offers absolutely zero business value if the system cannot reliably finish the operation without destroying the engine. The actual engineering win condition is measured across a full operational lifecycle. Success is defined by your cost per point efficiency over an entire season. That requires optimizing for total cost of ownership, operational durability, and system reliability at scale. Operators must recognize a stark business reality. You are not selling AI capabilities. You are selling EBITDA and profit margins. This brings us to the dual meaning of the word harness. It is the wiring that routes raw power from the engine to the wheels, but it is also the physical safety belt that protects the system from destroying itself. Strict governance guardrails and deep observability act as that safety harness. They allow your systems to operate at maximum computational capacity because you know anomalous edge cases will be caught long before they trigger a fatal failure. The harness is the sole determining factor in whether the heavy computational lifting of a frontier model actually translates into a profitable, survivable production outcome. This mechanical reality forces a shift in how you must view your own professional identity within the AI development lifecycle. The current developer mindset is largely reactive. Engineers sit as passengers in their own workflow, waiting for the next model release on a supplier's calendar, hoping new horsepower will fix their handling issues. As autonomous models increasingly take over the execution of the operational loop, the human relationship with the software changes. The AI engine has effectively become the driver. This represents your new operational position. You are the team principal orchestrating the entire operation from the pit box. Your duties are structural. You author the procedures, you monitor the telemetry, you dictate the overarching strategy, and you decide exactly when to make a tactical intervention. To succeed, you must stop obsessing over the raw capability of the model you are renting. Direct your engineering focus entirely onto the compounding architecture that you actually control. Long-term defensibility now depends on the continuous iteration and refinement of the racing team.